Our speaker for today is Dr. Sara Guerin. Dr. Guerin runs the Actuate Lab, a team of 10 multidisciplinary researchers in the Bernal Institute in the University of Limerick, Ireland. She currently works on both in silico and ex silico engineering of biomolecular crystals, primarily for application areas in eco-friendly sensing and pharmaceuticals. Dr. Guerin has been successful in securing over €2 million of funding from Science Foundation Ireland and the European Research Council for the development of organic piezoelectric device components. She currently works with a large number of international research groups in computationally predicting the electromechanical properties of novel molecular crystals. She has been awarded the British Association of Crystal Growth Young Scientist of the Year Award and the IEEE Dilip Das Gupta Memorial Award. She graduated in 2015 with a BSc in Applied Physics from the University of Limerick, going on to complete her PhD in piezoelectric modeling with Professor Damien Thompson. She is the 2023 Science Foundation Ireland Early Career Researcher of the Year. Thank you so much, Dr. Guerin, for joining us. The stage is all yours now.
So, welcome everybody. Thanks for joining me today to talk about my group's research on molecular crystals, and in particular what we call rational design of molecular crystals, which is using a combination of first principles modeling and crystal engineering principles to design crystals with the electromechanical properties that we want for the applications that we're interested in. So let me get my laser pointer. Yeah. So just a little bit about our group and what we do. So we are the Actuate Lab because we mostly work on sensing and actuating technologies. We're a hugely multidisciplinary group. We have three broad pillars that encompass modeling, molecular modeling, crystallography, so experimental crystal growth, and then electrical engineering to actually translate our materials into meaningful devices. Our focus is mainly on piezoelectricity, but we do work with other research groups on a variety of other functional properties, as you'll see throughout the talk. We're located on the west coast of Ireland, on what's known as the Wild Atlantic Way. Normally when you see pictures of the Wild Atlantic Way, it's lovely and sunny and beautiful from all of our tourist organisations. But I said I'd give you a picture of what it looks like on a normal day in Ireland, which is very cloudy and wet, but still very beautiful and very cool. So that's where we're located, but we work with researchers all around the world towards designing molecular crystals for these next generation technologies. A lot of what I talk about today is going to be part of our ERC funded research, which is the PB-Free project, where we're working on phasing out current piezoelectric technologies that rely on ceramics that contain either lead predominantly, but even for lead-free alternatives contain a lot of toxic elements like bismuth and niobium. So we're proposing molecular crystals as the next generation of customizable, eco-friendly, low-cost piezoelectric materials. And that's what a lot of the researchers in my group are currently working on under one of those three pillars. So what is piezoelectricity? So we have two piezoelectric effects that will take place concurrently in a material that doesn't have a center of symmetry. The word piezoelectricity comes from the Greek pieson, which means to press. So if we apply a force to our piezoelectric material, as you can see on the left, it will generate a surface charge. If you apply a periodic force, each of those surface charge pulses can be harvested as a useful voltage that can be used for different applications. In the same material, the converse piezoelectric effect also takes place, where if you apply an electric field through your material, it will start to strain and distort. So the broadest way that we can define piezoelectricity is that it converts mechanical energy into electrical energy and vice versa, as you can see on the left and the right. But crucially, our definition of piezoelectricity that it's a linear electromechanical coupling. That's particularly important for the energy harvesting applications that we work with, because it means the more force that you can apply to a material without breaking it, the higher the voltage that you're going to get out, the higher the power that you're going to be able to get out of your material. And that's important when we talk about engineering mechanical properties later in the talk. So in terms of applications, piezoelectrics are completely ubiquitous in modern day life, but in the form of lead-based ceramics. That's from very high-end medical devices, ultrasonics, scientific equipment. All of our AFMs have a lead-based ceramic in it to drive our AFM. Things like earthquake detection, but even musical greeting cards, some toothbrushes, dental equipment. All of these things contain a tiny piece of lead in them, which is, I suppose, concerning both from an environmental and a personal disposal standpoint. Today, I'm not going to talk about all of these applications. I'm going to focus a lot on this energy harvesting form, which is where we can harvest either directly applied forces, say from pedestrian traffic, or ambient mechanical forces in the form of vibrations, and convert them into useful electricity for applications like self-powered devices, self-powered medical devices, and wearable electronics and technologies such as that. So we are absolutely, I'm sure we're not even the first people who are currently in the room today, but we're not the first people to look at piezoelectric energy harvesting. Coldplay, as part of their world tour, are using what they call kinetic dance floors, but are really piezoelectric dance floors, to reduce the carbon footprint of their tour. So you'll see these people here, I can hear this music, but every step that they take is generating a pulse of electricity that can then be used to power, if it is of sufficient power, to power all of the electronics that are being used in that concert. And we're seeing this technology being used around the world a lot. We're seeing it in London and in Singapore, being used in nightclubs to, again, power everything in the nightclub. We're currently rolling out a project here in our own city to try and power things using piezoelectric tiles. So it's a really exciting technology to be involved in. But as I mentioned, the real problem with a lot of these technologies is that they contain a ceramic called lead zirconium titanate, or PZT. PZT has to be fabricated using lead oxide, which is very toxic even in its fabrication process. And that fabrication process, as for all ceramics, can be quite high temperature and take a lot of steps and require a lot of toxic byproducts or reagents. Lead-free piezoelectrics is a very large area of research, but unfortunately, a lot of the materials that are being proposed to take over from PZT that don't contain lead, as I mentioned, contain elements like barium, and niobium, and bismuth. So you can see here for KNN, which is a ceramic that is being pushed forward a lot as the next big piezoelectric material, does even more damage to the environment under these different headings than the ceramic that contains lead. So our goal is to really move away even from the phrase lead-free and to change that to eco-friendly piezoelectrics that do absolutely minimal damage compared to the oxides required to make these piezoelectric ceramics and the damage that they do to the environment over various categories. So biomolecular piezoelectricity, or biological piezoelectricity, really began to be discovered in the 1950s by Professor Aichi Fukuda, who unfortunately actually passed away a couple of weeks ago at the age of 102. He first discovered that bone, tendon, and many of these other things in our body had this piezoelectric effect. And that was really what started off this field. The majority of these materials lack a center of symmetry, which is a prerequisite for a piezoelectric response. So many biological materials, we never really know the magnitude until we investigate further, but have the structural requirements for this response. And it was around the 2010s that Andrei Kolkin, Lemonov, and a bunch of other groups started to look at technologically exciting piezoelectricity in this class of materials. One of the big materials that you can see on the left is a peptide called diphenylaniline. Diphenylaniline can form into many different nanostructures. It can be grown just as a single peptide crystal, and it started to have technologically exciting piezoelectric response for the first time, whereas until then it was more of a curiosity. Why is this phenomena occurring in these materials? But it was very, very low compared to ceramics and polymers and other materials. So up until 2010s, wasn't considered to be significant. We saw this paper on diphenylaniline, which was very significant in its response of up to 70 picocoulombs per Newton. And then we also had these kinds of bacteriophage energy harvesters. This was a Nature Nanotech paper where they managed to isolate a bacteriophage virus between two conductive substrates and generate useful power. So two significant studies that kicked this field off. Where we came into this in our group was in 2018, or prior to that, when we were actually doing the research in 2017, looking at glycine. Glycine is an amino acid. It's the smallest of the proteinogenic amino acids, very simple molecule. It crystallizes in 3 polymorphs, 2 of which are non-centrosymmetric, but in 2 different space groups. So it's a lovely case study because you have your negative control of alpha glycine, you have beta glycine, which hadn't been studied quantitatively until that point, and you had gamma glycine, which has a longitudinal piezoelectric response, which we really like for device applications. So if your crystal has a longitudinal response, that means you can have your simple sandwich type energy harvester, where you can have your piezoelectric material as a dielectric in the middle, sandwiched by 2 conductive electrodes. You apply your force by squeezing your material along that direction, and then you get your electricity out along that same direction. So we studied all of the amino acids, the 20 proteinogenic amino acids, with density functional theory calculations, and discovered this large response, this large shear response, meaning we had to shear the crystal to get out the piezoelectric surface charge in this beta glycine polymorph. So we were able to control the crystallization using ethanol or methanol, isolate this metastable polymorph, and confirm this high piezoelectric response. And this was the first time that a biomolecular crystal had a response of the magnitude of some of our piezoelectric ceramics like barium titanate. We then went on to design our energy harvester using our other polymorphs that had a longitudinal response. We placed our crystals between 2 electrodes and got about 650 millivolts peak to peak of useful voltage out of that crystal. What's really exciting about biomolecular crystals, or molecular crystals more broadly, is their dielectric constants. Their dielectric constants are 2 orders of magnitude lower than ceramics, which means you get a lot more voltage out per unit force and area for the same material. So already, without using any of our crystal engineering principles, we can outperform ceramics as regards to their piezoelectric voltage constants, which is relative to the dielectric constant of the material. We then went on to look at other amino acids. We looked at racemicity. So we looked at L-alanine, D-alanine, and then DL-alanine, a combination of the 2 different handedness of the molecules. And there we started to exceed a volt of peak-to-peak output for our energy harvesting devices. This is a single crystal of DL-alanine of 2 different shapes in our assembly. I'll show you what the full polycrystalline assembly looks like later in the talk. But this was a significant milestone of hitting 1.2 volts, which is kind of your LED lighting up level of electrical power. And now where we are now, having uncovered that these small biological molecules can have this property, what are the challenges? So I've told you some of the good things. They're cheap, they have favorable dielectric properties for energy harvesting applications, they're easy to grow, they don't have any byproducts during their formation, they decompose into basic molecules that can, that don't harm the environment. And as I'll show you, we can mold them into very diverse shapes. So firstly, what we need to do is increase their inherent piezoelectricity. And that's where our crystal engineering principles and our calculations are going to come in. Secondly, we need to control how these crystals grow, because in a large polycrystalline film, which you should be able to see here, we need to be able to orientate the crystals in a way that maximizes the piezoelectric response. And then thirdly, These are crystals that haven't been used in commercial technologies before, so we need to have that electrical engineering insight to integrate these crystals into medical devices and other applications. So you saw your single crystal of DL-alanine. This is our little sandwich type energy harvester. And when you look at that under the SEM, you see the chaos that is kind of this natural self-assembly of these materials. Because these crystals have a longitudinal response, you can think of each of them as having a little dipole. So a little electrical dipole here, when you apply your force, you're going to cause ionic displacement, amplify that dipole, and measure your piezoelectric response. So the natural way that these things grow means that you're not going to get your single crystal response in your polycrystalline film, because some of those arrows are going to cancel out, and your entire response of your film is just going to be generally an order of magnitude lower than in the single crystal form for natural self-assembly. For DL-alanine, with these needles, we were quite lucky. The single crystal response was 10 picocoulombs per Newton, so our unit is charge per unit force. That went down to about 4 picocoulombs per Newton in this polycrystalline film in the way they naturally self-assemble. So the first thing that we can do in order to overcome this problem of how these materials self-assemble chaotically and their inherent piezoelectricity is using predictive modeling. And we use density functional theory in order to predict the full spectrum of material properties for any molecular crystal. And that includes the anisotropy. So piezoelectricity is a hugely directional property. It is a 3×6 tensor in its full form. The number of non-zero components is dependent on the space group of the crystal, but up to 18 piezoelectric constants. And using our density functional theory, once we have your SIF, or your XORD structure, we can predict the full polarization tensor of our material, our dielectric properties, which I already explained are important, and then your elastic stiffness. So your full 6×6 elastic stiffness tensor. And then by multiplying / dividing out all of your tensors, you get the full spectrum of properties about your particular crystal, which is very exciting. The accuracy of this when we first benchmarked it back in 2018 was very good, and it's gotten even better since then compared to, say, nano indentation and various piezoelectric measurements, including piezo response force microscopy. And we've benchmarked it across a number of different categories of material. We started with our conventional, well-studied inorganic piezoelectrics, zinc oxide and aluminium nitride, and then moved on to peptide crystals, biominerals, co-crystals, where we combine 2 or 3 molecules together to form a multi-component crystal and modulate the properties. And as I highlighted, different chiralities and different polymorphs of the same crystal. So really high predictability for electromechanical properties, which means we can screen crystals. If we think of the CSD and all the molecular crystals that we work with, I'm sure there's many people in this talk who are currently working with molecular crystals who crystallize in monoclinic, triclinic, orthorhombic space groups. So we have these materials that exist already, and these models allow us to screen for high performance materials. What DFT also allows us to do, of course, is understand this phenomena. It's not just we want to identify materials, we want to understand why a material is piezoelectric, or, well, it's highly piezoelectric or lowly piezoelectric. And for the amino acids, it came down to very simple unit cell properties. So a lot of the amino acids crystallize in monoclinic space groups, as do a lot of our crystals. And we found that the magnitude of the monoclinic angle in the unit cell is what can make a crystal very piezoelectric. Because if you have a high monoclinic angle, you're going to have a very low shear stiffness. And again, we could directly quantify that using density functional theory. Low shear stiffness, the more flexible your crystal is, the more voltage, or the more, I suppose, electricity you're going to get out per unit force. So a flexible material or modulating the flexibility is a good way to modulate your piezoelectric response, because the more flexible a material, the more ionic displacement and the higher the natural piezoelectricity in the material. So this was our first design rule for piezoelectricity using density functional theory. But more recently, we've gone from piezoelectricity into even more complex materials. So this is a collaboration with the Mir group and with Sam and Cam, postdoc, where we were looking at photosalient crystals. So again, these are crystals with very unique mechanical properties. When you irradiate them with UV light, they start to twist and expand. So they can also be used as actuators. What we were able to do with the lovely crystal structures that the Mir group had was we were able to study the mechanical properties throughout this single crystal to single crystal transformation. So we were able to study or to model the XRD structure prior to irradiation, during irradiation, and after irradiation to help us to understand how these internal stresses release themselves or manifest through photosalience. And you can see here on the right that we get nice predictability versus experimental nano-indentation. So again, we can trust our models in terms of their quantitative predictability versus our various techniques for measuring these properties. So again, it's using DFT as this kind of nanoscale lens to understand what's happening to individual molecules, individual unit cells, to rationalize these complex phenomena. What we can also do is look purely at ferroelectricity. So a lot of molecular crystals also show ferroelectricity, which is a switchable electrical polarization. And our DFT predictions give us that polarization magnitude. This was a collaboration with the Bhumi Shankar group in India. And here we were able to, again, predict the material properties in every single direction along here for their particular molecule that was crystallized. And then we can rationalize how the displacements along various planes give rise to different piezoelectric responses. This was also our first stress strain curve. With very large crystals, is a very low accuracy stress strain curve. But we were able to predict the dynamic mechanical response of the crystal, where we can see the elastic and the plastic behavior of different mechanically interesting crystals. And all of this is in silico. So we can predict this about a molecular crystal before you even go into the lab, as well as if you have an exciting crystal and come to us after that point. Two things that we've developed in the past couple of years that are particularly exciting. The first on the left is this work that was led by Pierre Caussade on the modeling side, allowed us to kind of break through the size barrier of density functional theory to where we can predict the piezoelectric properties of any crystal, including these very large protein structures. This is a protein that I think is about 1.2 million atoms. It is 4 protein molecules that's crystallized in this unit cell and surrounded by water, as our proteins are both in crystallized form and for molecular dynamics. And again, you can see our predictability both for longitudinal and shear piezoelectric responses versus single crystal piezo response force microscopy. So really exciting that we're no longer limited in terms of size. This was using CP2K as a software for our predictions. We can also now, and this is our high accuracy stress strain curve, completely model the dynamic mechanical properties of a molecular crystal. So instead of taking all of your samples or all of your potential chemistries, doing compression testing, doing tensile testing, you can actually screen crystals for plasticity using relatively simple density functional theory calculations. And you can see where the crystal breaks, and you can track for piezo and ferroelectrics and that linear increase of surface charge with increasing strain, which is really lovely. What that brings us to is this really exciting point of crystal engineering, where we can work with really excellent chemists who can design crystals with certain synthons, with certain chemical properties, where they can pack together in different ways that modulate this property. So this was 2 of our collaborations with Gazet Group, where we were looking at co-crystals, combining molecules together and modulating their properties. And we get to this really fun point here from our journal cover, where we really can sit down and decide what properties do we want in our crystal? Do we want a metal ion? Do we want a particular biomolecule? Do we want a ligand? And then we were able to develop that into these functional MOFs. So our metal organic frameworks, where we could modulate the piezoelectricity of the MOF using the solvent molecule in the structure. So we showed over a variety of about 7 to 8 solvents that if the solvent is orientated in the pore, that means that all of those solvent dipoles are going to be lined up in a particular direction. And particularly for acetonitrile, which is our 4-Debi molecular dipole, that hugely amplified the piezoelectric response. So really exciting to modulate the properties of a MOF without changing the actual chemistry of the MOF itself, but by changing modeling and crystallizing the MOF with different solvents in the pores. So a really nice example of how we can modulate our electromechanical properties at the nanoscale. Now, that's the modeling. And the modeling set is great, and but it's very much at the single crystal level. We're predicting these properties at the single crystal level, and we can translate that, I wouldn't even say subjectively, but I suppose on a case-by-case basis to how it manifests in the polycrystalline phase. And when we first started growing amino acids, again, back in 2017, 2018, you can see how different the self-assemblies can be for very little chemical changes in the molecules themselves. So this is L-threonine, this is L-alanine, this is hydroxy-L-proline. You can see that L-threonine is very dense, which we like to see in our films, but you can see that the crystals are moving out in every direction. So you're not going to get a lot of orientation or a very high piezoelectric response. You can see the low density here in this alanine film, lots of gaps, which just makes it challenging to electrode and measure and work with those materials. And you can see a lot of warpage in these hydroxyproline films. You can also see a lot of kind of, I suppose, less perfect crystalline kind of gunk around the edges. So again, naturally self-assembling these materials onto substrates for device applications can be challenging, but we have now started to work with these polycrystalline aggregates and many other groups in order to drive them towards more technologically favorable self-assembly. Krishna Hari, my PhD student in my group, has been working towards controlling the crystallization parameters of small molecules in order to increase their density and their coverage and their orientation for piezoelectric applications. So you can see simple things here like changing the temperature at which we dissolve our materials. This is all for L-alanine. Hugely, this is a very dramatic example of a bad room temperature film, but you can see how the density increases with the supersaturation temperature without any change in the actual concentration of the solution. We can also try layering to increase the density, but you can see that's quite messy. We are getting increased density, but your coffee stain effect gets worse. You have big chunky crystals around the edge. It's a bit chaotic. But when we combine modulating our temperature with modulating our concentration, we get these beautiful dense full coverage over our films. These are all 2 centimeter by 2 centimeter aluminium substrates. And we get this perfect dense continuous coverage that we can use to integrate into a piezoelectric device. That then allows us to move from our initial energy harvesting prototype in 2018 to actually some meaningful, I suppose, energy harvesting devices. So this work was carried out by Saiv, who worked with us about 1.5 years ago, and she was able to advance from this type of energy harvesting into devices that can be used to detect different physiological responses. This is a common use of piezoelectrics, or common proof of concept for piezoelectric crystals. So what you can do is you can isolate certain voltage signatures to correspond to different physiological effects. So this is due to coughing. We can do that to bending, so in different limbs. That shear force will induce different piezoelectric signals. You can use it for respiratory sensing. So you can measure the breathing rate. You can also measure heart rate, things like that, if your material is sensitive enough. And within, I suppose, let's say 5 years, we were able to go from this kind of proof of concept into very meaningful devices, which is nice to see in this field. And the really exciting stuff, so this paper should be coming out in the next couple of weeks, so you can keep an eye out for that, is making these materials as versatile as ceramics. Another one of the reasons that ceramics are so popular, outside of their inherent properties, is that we can make ceramics into any shape that we want, any size, any thickness, and that's why they're in those kind of 50 applications that I showed you at the start of the talk, because we can make a disc, we can make a plate, we can make a stack, we can do all of these things. So our goal was to show that you could also have that dimensional versatility for molecular crystals. So we went back to our amino acids. You can see some various chemistries here. Some of these are hydrates, some of these are just single component. And we were able to fully control the dimensions of the sample. So depending on the application, and depending on the dimensions that we want, we can get these lovely, dense, continuous piezoelectric components. And then we can embed, whatever chemistry and properties we want using the actual molecules itself. So this methodology is independent of the crystal chemistry. We can do it with any amino acid or peptide crystal or co-crystal that we've tried so far. And we get this very repeatable, naturally occurring unpoled piezoelectric materials, which is really exciting. What these look like under the SEM is you see these kind of dense polycrystalline meshes. And what might be interesting, because I assume many of the people here do work with single crystals, is on the surface, we actually prefer this lovely, messy morphology. If when we crystallize a material together, we get lovely single crystals that we would love for our XRD or for any single crystal application, actually doesn't benefit us in the polycrystalline form, because many single crystals means many grain boundaries. Many grain boundaries means very many fracture points. So these two on the bottom actually correspond to quite fragile molds. So they couldn't be used for direct force application. They could harvest vibration, they could harvest non-contact mechanical energy, but would be too fragile, because you can see these are going to shatter when you apply a force to them into all of their respective single crystals. But we actually like this really muddled morphology, where at least on the surface, your single crystals are morphing together and nucleating into each other to form this messy, cohesive polycrystalline structure. And then beneath that, you have your orientated crystals that again are morphing together into 3 dimensions. Now we can control the relative density of these materials, again, just by controlling our concentration. So we can control the porosity and things like that for different applications, purely by just modulating our solution, our solvent in our crystallization bath. So you can keep an eye out for that one in the coming weeks. You can see the inherent piezoelectricity. This is a lot of data. You don't have to worry about all of it, but it's just showing how we can modulate and control the thickness and the piezoelectric response. This is a particular batch that had quite low piezoelectricity. You can see between 1 and 2 picocoulombs per Newton. But this is purely with no post-processing. So this is just the natural self-assembly of the materials. Once we control the orientation, reduce our surface roughness, all of those post-processing, we get back up to our single crystal response of around 10 picocoulombs per Newton, which again is very exciting. In terms of energy harvesting, we see this is all for glycine and then one for hydroxyl-proline. We're already exceeding those single crystal voltages that I showed you from 2018 in this polycrystalline form. So we hit our 1.2 volt benchmark. But even more crucially, as I hinted at before, it's for very low piezoelectricity. So this is for a sample that only has 1 picocoulomb per Newton, which is lower than any commercial piezoelectric. But we're getting voltages out that match or exceed ceramics or polymers. And this is due to this piezoelectric voltage constant that I flagged here. So even for very low performing piezoelectrics, as we would normally screen for them, molecular crystals have so much more potential in terms of voltage and current generation for this energy harvesting applications. And then finally, you can look at the study, which again should hopefully be coming out in the next couple of weeks. We can put that whole story together in terms of engineering a crystal from the bottom up using our crystal engineering principles. This is a co-crystal that we're going to be publishing quite soon. It is lysine and mandelic acid, and it crystallizes together. This is it after compression testing. We can crystallize it together in our molded structure. The morphology crystallizes together, and you can see all the individual plates there that morph together to form our macroscopic self-assembly. And you can see here how those bigger plates morph together in this larger polycrystalline structure. What was really fun about this that we actually discovered during the review process is that because we have plates orientated the way that we like, which is where we can harvest our longitudinal piezoelectricity and everything is perpendicular, but these crystals are actually orientated at 45 degrees, which gives us an opportunity to harvest the shear piezoelectricity in these materials. So what that is particularly important for molecular crystals is because I was talking about monoclinic angle earlier, and that monoclinic angle gives you low shear stiffness, which means you're always, well, generally speaking, going to get more voltage out of a biomolecular crystal when you apply a shearing force in a direction permitted by its space group, compared to just a longitudinal response. So by molding these materials together and by inducing this kind of constricted self-assembly, we're able to harvest the higher shear response, but with our longitudinal measuring techniques or harvesting methods. So a really nice example of designing a co-crystal from the bottom up to have the particular piezoelectric properties that we want, using our growth methodology, and then forming this piezoelectric element that could be put in to a piezoelectric device. The next thing that we need to do is, I suppose, the elephant in the room with these, but something that's quite common with a lot of piezoelectrics, is that they're water soluble. We grow a lot of our crystals from water, and that means we need to protect them from water for our device applications. And we did this for this co-crystal. We showed that when you broke the crystal apart, like very forcefully broke the crystal apart, again, we saw different magnitudes of piezoelectric response, which correlated to those relative orientations of the crystal. So if you got a dominant crystal face that facilitated shear piezoelectricity, you got a higher piezoelectric response. If you got pieces that predominantly showed that or the perpendicular orientation, you got a lower piezoelectric response. And then we took those pieces, we took our molds, and we insulated them in our low dielectric polymer. Low dielectric means that we're not going to lose any of our piezoelectric response, and the surface charge can move through the polymer and still be harvested. So you can see the crystals are almost laminated here in this SEM image, and they've been completely isolated from the outside. It increases their plasticity, which we like. You can see our coated crystal starts to deviate and move into more of a plastic zone much earlier. So it also improves their mechanical properties. And then when we carry out our dissolution tests, you can see that for our uncoated piezoelectric element, we get dissolution over 24 hours, but for our polymer coated molecular crystal element, we get no dissolution after 24 hours. So fully performing, bottom-up designed, insulated, polished, eco-friendly piezoelectric sensor for the first time. So to summarize, what our group is working on, and I think what the field as a whole is moving towards, is truly eco-friendly materials. And for us, that really comes down to biomolecular or eco-friendly molecular crystals, because, as many of us know, we can now take this functional property and combine it with everything we know from as regards co-crystallization, crystal engineering, everything that we've done for pharmaceuticals, everything that's being done by many of our big molecular crystal groups in terms of engineering mechanical properties, plasticity, self-healing. We can take all this knowledge and use it to develop this next generation of piezoelectric devices, so that when finally we get a sunset date for these kinds of piezoelectric elements that keep being pushed out because we don't have an alternative to PZT or to any ceramic, we're able to modulate the properties and also tailor them to applications. We can use a plastic crystal for a flexible application. We can use a rigid crystal for our more kind of ceramic, thick-based applications, for resonators and things like that. And it really opens what I keep calling, I suppose, a Willy Wonka chocolate factory of different electromechanical applications that we can tailor these methodologies to. And the exciting thing that I like to finish with at the end is this collaboration that we carried out with Vikram Pakrashi in University College Dublin, where we started to validate these materials for structural health monitoring. So we managed to outperform PVDF, which is the leading commercial piezoelectric polymer, for its sensitivity in detecting damage in structures. So what we have here is a leak index, which is just a marker of sensitivity. And we have different leak states here, where we introduce different leaks into a pipe system, and the vibration that travels along the pipe from the different sizes of leak travels to your piezoelectric sensor, in this case, which was made from your cheap, low-cost amino acid, it crystallizes from water. We were able to outperform those materials. So I think there's huge potential here. It's becoming a bigger and bigger, more exciting field, and lots to do using our crystal engineering skills that a lot of us are currently working on. So with that, I would like to thank everybody. Good models particularly require a lot of collaboration. So a huge thanks to everybody in UL, in our pharmaceutical research center, all of our experimental collaborators from around the world who give us their crystal structures with these exciting properties to model and work on, and also to evaluate our crystals in different piezoelectric technologies. This is my fantastic group, my PhD students and postdocs who do all the hard work. Our group is funded by the European Research Council and Science Foundation Ireland, and all of our modelling takes place on our national supercomputer, which is run by the Irish Centre for High-End Computing. So thank you all for listening. I will leave you with this lovely cartoon that was made for us by the Royal Society of Chemistry and Air and Science on piezoelectric energy harvesting, and I look forward to your questions. Thank you.
Thank you so much, Dr. Guerin, for this wonderful lecture.